Today in solid state physics, we are going to discuss a very important concept of Brillouin zones. Actually, Brillouin zones are the regions in the reciprocal space of a crystal lattice which helps to describe the allowed energy states of electrons in the crystal. In fact, this is important in solid state physics for understanding the electronic band structure and determining the properties of the crystal like electrical conductivity, thermal conductivity, optical properties, transport properties, and so many more. Okay. Actually, first of all, we will know what is this Brillouin zone, and then we will learn about how it is constructed. Actually, in 2 consecutive lectures, the idea of Brillouin zone will be completed. In this first lecture on Brillouin zone, we will see only about the construction of Brillouin zone in case of the 2-dimensional lattice, or you can say plane lattice. But we will talk about its construction in the actual lattice, which is 3-dimensional, in the second lecture on this. Okay. So let us first of all try to know what is this Brillouin zone. Actually, while studying the direct lattice, you have studied definitely the Wigner-Seitz cell. Okay. And first of all, you should know that these Brillouin zones are simply the Wigner-Seitz cells in reciprocal lattice space. Okay. So whenever you will talk about the Brillouin zone, you have to think about the reciprocal lattice space, or you can say the Fourier transform of the direct lattice space, and in that case we can discuss only this Brillouin zone. Okay. Actually, the Brillouin zone concept arises from the periodicity of the crystal lattice in a real space. You know, when the crystal potential is Fourier transformed into reciprocal space, it creates a periodic array of points which are called reciprocal lattice. And these Brillouin zones, as I have told you, are the Wigner-Seitz cells of the reciprocal lattice, which means they are the regions of a space around each reciprocal lattice point that are closer to that point to any other reciprocal lattice points. Okay. So you can see how this Brillouin zone can be constructed or can be defined. See this figure. Actually, all these dots which I have shown in this figure represent the reciprocal lattice points. These are reciprocal lattice points. Okay. And so this space you can say is a reciprocal lattice space. I have shown actually these points in a plane, but these points may be in 3-dimensional space. But here at present I have shown this in a plane, that is on the plane of the paper. Okay. And now consider one of the reciprocal lattice point. Let us say this is a reciprocal lattice point. Now you have to think and you have to seek, you can say you have to seek, you have to choose all other reciprocal lattice point which are closest to this point which I have selected. So see, let us say that this is a reciprocal lattice point which is closest to this point. So join these 2 points. Similarly, if you consider that this is another lattice point, I am marking it here. This is the first reciprocal lattice point which is closest to this reciprocal lattice point lying at O. This is the second, this is the third, this is the fourth, this is the fifth, this is the 6th, this is the 7th, this is the 8th. Okay. These are the reciprocal lattice points which are closest to this reciprocal point lying at O. It means you can say that there is no other lattice points in this reciprocal lattice space which are closer to this lattice point at O than these lattice points. Okay. Now, to find the Brillouin zone, you have to join this reference lattice point to all those points. So I am joining here. You can see the point O to 1. Again, you have to join O to point 2, O to point 3. In this way, you have to join all the closest reciprocal lattice point to the point O. Okay. Now let us draw the planes perpendicular to these joining lines passing through the midpoints of the line. You can see this is the joining line O1, and this line which I have marking here, this is not a line but it is a plane. But as this plane has been shown in just a plane, so it appears like a line. But you should say that this AB is what? This AB is a plane passing through the midpoint joining the two reciprocal lattice points lying at O and at 1. Okay. Similarly, draw the another plane passing through the midpoint of the another joining line O2. Okay. And this is your let us say plane AC. Similarly, you can draw a plane marked as CD which passes through the midpoint of the line joining O to 4, and this also passes through the midpoint of this line. In the similar manner, we draw this plane, this plane, this plane. All these planes are drawn passing through the midpoints of the joining line to the reciprocal lattice point which are closest to this reference lattice point lying at O. Now, these planes intersect one another, and you can see you have to actually locate the region bounded by the boundary of these planes. So, I am marking here the region which are bounded by these planes. This shaded region you can see, this is the region which is actually bounded by these planes. Actually, this region is the Wigner-Seitz shell in reciprocal lattice space. Reciprocal lattice. And this is the smallest volume shell, and this smallest volume shell is called the first Brillouin zone. Okay. So the region you can see A, B, C, D, E, F, B. This actually represents the first Brillouin zone. So this is first Brillouin zone. BZ I have written it for Brillouin zone. Okay. Now, after constructing the first Brillouin zone, we can easily construct the second Brillouin zone, third Brillouin zone. Actually, the next shell surrounding the first Brillouin zone is called second Brillouin zone, and the shell surrounding the second Brillouin zone is called the third Brillouin zone. Okay, and in this way you can construct all the Brillouin zones. Okay, so I think we have understand what is this Brillouin zone and how this will be constructed. Actually, when we consider that a wave vector is propagating starting from this point O, then this wave vector will get reflected. It suffers Bragg's reflection from these planes. So actually these planes are what? These planes are called Bragg's reflecting plane. These are Bragg's reflecting plane. So you can also define this Brillouin zone in this manner, that Brillouin zone is the region bounded by the Bragg reflected planes. When you say Bragg reflected plane, then what does it mean? It means the wave vector will suffer Bragg reflection when incident on these planes. Let us see. I am marking here a wave vector which is incident on this plane and gets reflected and suffers Bragg reflection. If Bragg reflection will take place from these planes, only then you can say these planes are Bragg reflecting plane. And the region bounded by these Bragg reflected planes is actually called the first Brillouin zone. Okay, these are called first Brillouin zone. And if any wave vector does not suffer reflection from these planes, it means that such a wave vector does not suffer Bragg reflection. Okay. So I think you have understand what is this Brillouin zone. But this idea of Brillouin zone and its construction will be very clear to we when we will take a proper example. So as I have told you in this first lecture on Brillouin zone, we will consider the construction of the Brillouin zone of a simple square lattice. That is, we are talking about two-dimensional lattice, particularly the square lattice, and we will try to find the Brillouin zones in this case. And after this calculation, your concept regarding the construction of Brillouin zone will be crystal clear. So let us see how we can construct the Brillouin zones of a simple square lattice. As you know, the primitive translation vectors of a simple square lattice are given like this. Vector A is equal to AI and vector B is equal to AJ, because here modulus of vector A is equal to mod of vector B, because we are considering the square lattice. Okay. So this is your first primitive translation vector AI, and this is the second primitive translation vector AJ. Since the lattice is two-dimensional, so there will be not AK. Okay. And these are actually the reciprocal translation vector of the direct lattice. Now, according to the definition of reciprocal lattice, you can say that the corresponding translation vectors for the reciprocal lattice will be what? So, if A star is the reciprocal lattice translation vector for the corresponding to the direct lattice translation vector A, then according to definition, this A star will be equal to 2 pi over A times I. Okay. And similarly, the reciprocal translation vector for this translation vector B of direct lattice, which is denoted by B star, that will be equal to 2 pi over A J. You can also write 1 over A I for A star and 1 over A J for B star. It means according to the definition, this factor 2 pi may be replaced by 1. Okay. Now, we have to actually find the condition for Bragg's reflection, and actually in the previous lecture you have already studied the condition for Bragg's reflection or the vector form of Bragg's law. So according to the vector form of Bragg's law, or when Bragg's reflection takes place, you have actually studied that this condition is written as 2k dot g plus g square equal to 0. This is the Bragg's condition for taking diffraction or reflection. Okay. And so to apply the Bragg's condition, we have to find the wave vector and the reciprocal lattice vector. In this expression, you know, k represents, kappa actually represents the wave vector, and this capital G vector represents the reciprocal lattice vector. So to apply the Bragg's condition, we have to define these two vectors. You know, the reciprocal lattice vector is defined as G equal to HA star plus KB star plus LC star. But here we are talking about the two-dimensional lattice, so this third term will be 0. So I have written G equal to HA star plus KB star. Okay? But you can see A star is 2 pi over AI, B star is 2 pi over AJ. So let us substitute the value of A star and B star as we have defined, and so you can say that this reciprocal lattice vector capital G is equal to what? This is 2 pi over A HI plus kg. Okay? And you know that actually this H and K are integers. Now we will define the wave vector K. As this wave is traveling in this plane, so it will have only two rectangular components. Third one will be 0. So when wave vector lies in a plane, you can write this kappa, which represents the wave vector, is equal to kappa xi plus kappa yj. Okay? Now we can see what will be the result when we will apply the Bragg's condition. When you say Bragg's condition, it means this condition is used to find the Bragg reflecting plane, which plane will actually provide the Bragg reflection of X-ray. You can obtain from this relation or from this equation. Okay, you know that this Bragg's condition actually says that 2 kappa dot G plus G square is equal to 0. Okay, and you can see we have just defined the two vectors kappa and G. So let us substitute the values of kappa and G here, and after putting their values, what will be our result? You can easily see. Okay, you can see kappa G is this much and kappa is this much, and in first term there is 2 kappa dot G. So this will be 4 pi over A kappa xi plus kappa yj dot hi plus kj. Okay, and plus G square, and you can see the square of the modulus of this vector G will be what? This will be 4 pi square over A square plus H square K square. Okay, so this is 4 pi square over A square times H square plus K square, and that equal to 0. Now you can see, you can take this 4 pi over A as a common factor. Okay, and since in RHS there is 0, so that will be removed, and your result will be what? Let us find the scalar product of these two vectors. This is just a simple calculation. You can see the scalar product of these two vectors will be what? That will be H kappa x plus K kappa y, and here after taking this 4 pi as a common factor, the remaining term is pi over A times H square plus K square, and that is equal to 0. Okay, and so you can say that H kappa x plus K kappa y is equal to minus pi over A times H square plus K square. Okay, now as we have seen that the K values which are Bragg reflected are obtained by considering all possible combinations of H and K. Substituting the values of H and K in a particular fashion, you can obtain all the values of K which will suffer Bragg reflection. And in this regard, we will actually have to consider two cases. In first case, let us see what are our consideration. Actually, in first case, we will see the two situations. In first situation, we consider the integer h is equal to plus minus 1. We consider it. And we take k equal to 0. So, when you will take h equal to plus minus 1 and k equal to 0, then what will be this equation 1? Since k has been taken 0, so this second term will vanish, and h is taken plus minus 1, so in LHS there will be plus minus kappa x, okay? And in RHS, h is plus minus 1, so this will be h square will be 1 and k square is 0, okay? And so this will be simply minus pi over a. So you can see our result in this condition will be plus minus kappa x equal to minus pi over a, okay? Or you can write this equation in this manner, that kappa x is equal to plus minus pi a. And in this condition, you can take any value of kappa y. Its value is arbitrary. It depends on you. Why? Because we have taken k equal to 0. So, what is the value of kappa y? That does not matter. You can take any value of kappa y. So, here kappa y is arbitrary, but the value of kappa x is restricted. It is equal to plus minus pi over a. Okay. Now, our second choice is just opposite to the first choice. In our second choice, we take h equal to 0. In first choice, we have taken k equal to 0, and now we are taking h equal to 0. And k equal to plus minus 1. In first choice, we have taken h equal to plus minus 1, but now we are taking k equal to plus minus 1. And substitute these values in your equation number 1. What will be your result? Here h is 0, so first term will vanish. K has been taken plus minus 1, so in LHS there will be plus minus ky, and in RHS h is 0, but k has been taken plus minus 1, so in RHS there will be minus pi over a. So our result is kappa y equal to plus minus pi by a. In this case, actually you can take any value of kappa x. It means the value of kappa x is completely arbitrary. So in this condition, we have 4 equations. Actually, this equation represents 2 equations by taking the sign plus and minus. These are 2 equations. Similarly, this second equation also represents the 2 equations. And all these 4 equations actually represents the 4 straight lines. These are equations of a straight line. You know, y equal to c. This is an equation of a straight line. X equal to c. This is also equation of a straight line. Y equal to c. This actually represents a straight line which is parallel to the x-axis. This is parallel to x-axis, okay? And x equal to c, where c is constant, this represents a straight line which is parallel to y-axis, okay? So, we can draw these straight lines. And so, let us see this figure for this. You can see, I have taken this point O as origin, okay? This point O, you can see this figure, this point O shown in this figure has been taken as origin, okay? And you can see this straight line, which is I am just redrawing. This straight line is represented by the equation what? This is represented by ky equal to pi by a. Actually, here we are going to plot kappa y in against of kappa x. Kappa y, this is at the place of y coordinate, kappa x is at the place of x coordinate. Okay, so in this xy plane, we are going to plot kappa y in against of kappa x. Kappa y, which is the y component of wave vector, and kappa x is the x component of wave vector. Okay. Now, kappa y equal to pi by a. This represents a straight line which is parallel to this kappa x axis. Okay, and at any point on this straight line, the value of kappa y will be equal to pi by a. So the straight line which I am marking here by this P1, P2, this represents the line kappa y equal to pi by a. You can check it. Okay. Similarly, this line Q1, Q2, see the figure Q1, Q2. This represents the straight line defined by the equation kappa y equal to minus pi by a. Okay. Now the remaining two equations are what? Now the remaining two equations are kappa x equal to plus minus pi by a. And you know, these two straight lines will be parallel to actually the kappa y axis. So see this line, I am marking it here by R1, R2, R1, R2. This is the straight line defined by the equation kappa x equal to pi by a. This is the straight line, you can see. Okay, and similarly, this straight line S1, S2, S1, S2. This straight line is defined by the equation kappa x equal to minus pi by a. Okay, this is just an elementary coordinate geometry. You know the equation of a straight line, y equal to plus minus c and x equal to plus minus c. Okay, you can see these four straight lines intersect one another at these points. This A is a point of intersection, B is another point of intersection, C is the third point of intersection, and D is the fourth point of intersection. Okay? And so, after the intersection of all these four straight lines, we get a square. You can see this A, B, C, D. A square is formed after the intersection of these four straight lines. Okay? In fact, this square whose side length will be what? You can see. Actually, this distance is pi by a, you know. This is pi by a. And this distance is also pi by a. I am not writing minus pi by a, I am writing only the absolute value. So, the side length AB is equal to CD, this is equal to BC, and this will be equal to DA, and all these are equal to 2 pi by a, you can see. So this is just a square of side length 2 pi by a. Okay. In fact, this square is called the first Brillouin zone of the square lattice. Okay. In fact, you can see here is a reciprocal lattice point, this is another reciprocal lattice point, this is another, and this is another. And this is the smallest region, which is lying in which any other lattice point is the closest lattice point to the lattice point at the origin. Okay. And if you consider the wave vector, you can see this figure I have shown here, the different wave vectors. This is kappa 1, this is kappa 2, this is kappa 3, this is kappa 4. When you will take this these wave vectors, and these wave vectors will get reflected from the boundary of this square, okay, from the boundary of this square. And so the boundary of this square is nothing, these are simply the Bragg's reflecting plane, okay. And I think you have understand how we can construct the first Brillouin zone of a plane, a square lattice. Actually, all these things I have mentioned it here. You can see that in first case, all these four equations represents straight lines, as you have seen this in this figure. And I have mentioned those facts for your convenience. You can note down these things in your notebook. The square ABCD bounded by these four lines is called first Brillouin zone, which is a square of side 2 pi by a. Taking the origin as shown, all the k vectors originating from it and terminating on these lines will produce Bragg reflection. Okay, that will suffer Bragg reflection. Now let us consider the second case. In second case, we will take again a particular choice. In second case, we consider that h is equal to plus minus 1 and k is also equal to plus minus 1. So after this choice, what will be our equation number 1, which actually refers the Bragg's condition, or when Bragg's condition will get satisfied, that is represented by this equation. Now according to our supposition, we have considered h equal to plus minus 1 and k is also plus minus 1. So let us substitute these two values here. So the first term will be what? That will be plus minus kappa x. Second term will be also plus minus kappa x in LHS. And in RHS, h and k both are plus minus 1. After squaring, those will be 1. So this in RHS you will get 2 minus 2 pi over a. Okay. So our result is plus minus kappa x plus minus kappa y, that's equal to minus 2 pi over 2 pi by a. Okay. Now we can have the four equations again. Actually this equation represents the four equations by taking the proper sign. You can see, if you consider the both positive sign in LHS, what will be our equation? Then taking only the positive sign in LHS, our result will be kappa x plus kappa y equal to minus 2 pi by a. Okay? And so you can write kappa y equal to minus kappa x minus 2 pi by a. And you can see this is nothing, this is equation of a straight line in slope form. This equation is in this form. This is y equal to mx plus c. Here m, which represents the slope of the straight line, that is equal to minus 1 in this equation, minus 1. And so this will make an angle of 135 degree to the positive x-axis, or you can say it will make angle 45 degree with the negative x-axis. And the constant c is negative, so its intercept on y-axis or kappa y-axis will be in the negative side. Okay. Now take both negative sign in LHS. So this will be minus kappa x minus kappa y equal to minus 2 pi by a. So minus in both sides will cancel out, or your result will be kappa x plus kappa y equal to 2 pi by a. And hence you can say that this kappa y is equal to minus kappa x plus 2 pi by a. You can see this also represents a straight line having the same slope minus 1, but this constant, this intercept on kappa y axis 2 pi by a is positive for this straight line. Okay. Now take plus and minus sign alternately in this equation. So if you will take plus kappa x and minus kappa y, and that equal to minus 2 pi by a, you can take it, you can see it here. And so kappa y will be equal to kappa x plus 2 pi by a. This is a equation of a straight line, you can see in slope form, and the slope of this straight line is plus 1, and its intercept on kappa y axis is plus 2 pi by a. So it will intersect the kappa y axis in positive direction. Now take plus minus in minus plus in LHS. So this will be minus kappa x plus kappa y equal to minus 2 pi by a. And so kappa y will be equal to kappa x minus 2 pi by a. This is also equation of a straight line in slope form, and the slope of this straight line is also plus 1, but its intercept is 2 pi by a on kappa y axis in negative side. You can see all these 4 straight lines in this figure. I have shown it here, you can see. See this straight line. The straight line which I am marking here, let us say this is T1, T2. This is the straight line defined by the equation kappa y equal to kappa x minus 2 pi by a. You can see the intercept of this straight line on the kappa y axis is in negative side. Okay, you can see this is the negative side here, and it intersects this line here, you can see. And so the distance of it from here, this is actually pi by a, and this distance is also pi by a. So this is 2 pi by a. Okay. Similarly, this straight line, let us say u1, u2. This straight line is represented by the equation, you can see kappa y equal to kappa x plus 2 pi by a. Okay. Its intercept on the kappa y axis is this much. This is actually see here, this distance is actually 2 pi by a. Okay. Similarly, this equation, this straight line, let us say V1, V2. This V1, V2 has been represented by the equation kappa y equal to minus kappa x plus 2 pi by a. Okay. And this equation kappa y equal to minus kappa x minus 2 pi by a, this is the straight line represented by, let us say, Z1, Z2. Okay. So these are the straight lines which we have obtained analytically, and we have plotted in this graph. Now you can see these straight lines intersect one another at which points? This is one of the point of intersection. Okay. Here there is a point of intersection, this is 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 point of intersection, and this is point of intersection. Actually, this region which I have marked here, you can see the region number 1, region number 2, region number, let us say 3, and this 4. Actually, all these regions are called the second Brillouin zone. This is called second Brillouin zone. Okay. So the region marked by 1, 2, 3 and 4, this is called second Brillouin zone. So I think you have clearly understand how we can construct the first and second Brillouin zone in case of a plane square lattice. Okay. Actually, in this manner, we can also construct the third Brillouin zone, the fourth Brillouin zone, and so on. Okay. So I have what I have explained, I have written here for your convenience, because our aim is to not only to understand the concept but also to write a good answer in your examination. And so I have prepared a good notes for you too. And so you must write these things in your notebook, revise it and write down in your examination. You will get certainly good marks. Okay. As what we have learnt, I am just giving a reading for that. You have seen that in second case, the equation is plus minus kappa x plus minus kappa y equal to minus 2 pi by. Actually, as you have seen that this is not a single equation, but it represents 4 equations, and all those 4 equations which I have marked here, this is equation 1, equation 2, 3 and 4, all these represents the equation, all these represent the straight lines, okay, and which I have shown in that figure. So these lines are plotted. The additional area bounded by these lines are ADE, CDF. You can see ADE, okay, CDF, which I have marked by 2. Again, CBG and BABH. These additional areas are actually called the second Brillouin zone. So this additional area is called second Brillouin zone. And as I have told you, in the similar manner, the other Brillouin zones are constructed. But for examination point of view, there is no need to construct the third, fourth and so on Brillouin zones. You have to limit it yourself only up to the second Brillouin zone. Okay. And as we have just discussed in the beginning of this lecture, that the boundaries of the Brillouin zones represent the loci of K values that are Bragg reflected and hence may be considered as the planes. The boundaries of the first zone represent the reflecting planes for the first order reflection. This is a remarkable fact. When you are talking about the first Brillouin zone, so you can say from the boundary of the first Brillouin zone, Bragg's reflection will take place. But what will be the order of that Bragg's reflection? Actually, if Bragg reflection takes place from the boundaries of first Brillouin zone, the order of Bragg reflection will be 1. And in the similar manner, you can say that if Bragg's reflection takes place from the boundary of the second Brillouin zone, the order of Brillouin zone, the order of Bragg reflection will be 2. And in this manner, you can say if the reflection is taking place from the boundaries of the third Brillouin zone, then there will be third order maxima. Okay. But if a K vector is not terminated on the zone boundary, then that will not produce Bragg reflection. Okay. So in this condition, you can easily say that we can decide that Bragg reflection will take place or will not take place. What will be the criteria? Actually, the Brillouin zone pattern can be used to determine the X-ray diffraction pattern. And if you know the X-ray diffraction pattern, you can know about the Brillouin zone. Okay. So this concept of Brillouin zone is a very strong tool to study the X-ray diffraction. And this is not only used in X-ray diffraction, as I have told in the beginning of this lecture, that actually the formation of energy band in a solid, that is also discussed in terms of the Brillouin zones, and also the motion of electron in a periodic potential inside the solid is discussed and explained if you have idea of Brillouin zone. Okay, so the concept of this Brillouin zone is very crucial, very important in the study of solid state physics. Okay, now this is the end of this lecture, and in my second lecture on this Brillouin zone, you will see how we can construct the Brillouin zones of the simple cubic lattice, the BCC lattice, the FCC lattice. Okay, and that will be actually also a very useful and very joyful class for you. Thank you very much.